lecturer. Guys, Madam Mariam here. So today we are going to continue with the topic of Lensmaker equation. What is Lensmaker equation? It relates the focal length of the lens to the radius of curvature of its two surfaces. Radius of curvature is actually the center of the lens. So let's say I have a convex lens here. Draw the normal line or draw the center line. Okay, so from here towards the center, this is called center of curvature or radius of curvature of the lens. It can be on this side, it can also be on the other side, depending on where the light passes through. So if let's say the light passes through from left and it hits the first surface here, this will be my R1, inner side of the lens. That will be the center of curvature. But if let's say the light hits the second surface, which is this part here, the center of curvature will be on the inner side, which is this part. So this will be my R2. Now remember, this is the back of the lens, whereas this is the front of the lens. So my radius of curvature at the back of the lens will be positive value, whereas at the front of the lens it will be negative value. The same as your focal length. If it is at the back, it is positive. If it is at the front, it is negative. Okay. Alright. So let's look at the equations. The lens can be placed in any types of medium. Depending on the type of medium the lens is placed, the equation varies. If the lens is in air, the equation will be 1 over f is equivalent to n minus 1. N will be your refractive index of the lens material, and times 1 over R1 minus 1 over R2. So R1 will be the radius of curvature for the first surface of the lens. R2 will be the second radius of curvature for the second surface. If let's say the lens is not in air, it's in other media, the equation will be 1 over f is equivalent to n2 over n1. N2 will be the refractive index of the lens material, whereas N1 will be the refractive index of the medium. So for example, if the lens is in oil, so light hits the oil first. So this will be my N1, and it goes to the lens. So once it hits the lens material is my N2. Okay, and then minus 1 times 1 over R1. Again, R1 is the radius of curvature of the first surface of the lens, minus 1 over R2. R2 is the radius of curvature for the second surface. So make sure you identify first whether the radius of curvature is positive or negative. Let's take an example here. A diverging lens has a convex surface of 30 cm and 20 cm. So if you still remember, this is the diverging lens where the insides are much thinner as compared to concave or convex lens. As compared to convex lens. Right? So which is the concave surface and which is the convex surface? Depending on the direction of the light. So light passes through from left to right, meaning it passes through from here. Okay, so the first surface it will hit will be, this is the first surface, a concave surface. So when it hits the concave surface, the radius of curvature will be here, inner side of the surface. So this will be my R1. And since it is at the front of the lens, concave surface value is 20 cm. So my R1 will be negative 20 cm. Hold on. And for R2, that will be the second surface it hits. So this is the second surface, and it is a convex surface. So the radius of curvature is on the inner side. This will be my R2. Since it's at the back of the lens, value will be positive. So my R2 is at the convex surface. So convex surface will be 30 centimeter. So positive 30 centimeter. Put it inside the equation. Since this lens is in air, it's not mentioned that the lens is in another type of medium. So we can assume that it is in air. So in air, we can use this equation n minus 1 times 1 over r1 minus 1 over r2. So put in all the values and you will get negative 24 centimeter. Right? Okay, so I want you to do this yourself. Okay, you can check the answers with me later on. So these are the sign convention for thin lenses for you to refer to. Possible, try to understand them, memorizing the values, the equations, right? So let's go to the final subtopic, which is spherical mirror, locating images and mirror equation. So we've learned about lenses. If you still remember, we have two types of lenses, which is convex and concave. So mirrors are the same also as lenses. It has two types, which is convex and concave mirror, but the functions are opposite of each other. So it is opposite of lens. Now, what do I mean by opposite? Okay, for mirror, okay, for convex mirror, instead of converging the light, it reflects back the light. So you can see here, whenever the light hits, it will be reflected back. Okay. Whereas for a concave mirror, it is reflected as well, but towards the inner side of the lens. So at one point, the light will be converged here. Whereas for convex mirror, the light will be converged here. So this is the focal length of a convex mirror, whereas this is the focal length of a concave mirror. Let's look at a much clearer example here. Right, so like I've mentioned before, for concave lens, the focal length is at the front of the mirror, whereas for convex lens, the focal length is at the back of the mirror. If you still remember, for lenses, if it is at the front, what will be the focal length? Positive or negative? Or if the image is at the front, would it be virtual or real, if you still remember? Okay, because I'm going to differentiate between lens and mirror here. Yes, at the front of the lens, the value will be negative, whereas at the back of the lens, the value will be positive. So this is opposite as mirror. For mirror, front is positive, whereas back is negative. Meaning, for concave, instead of negative at the front, it is positive F. For convex mirror, at the back, the value will be negative F. Okay? So it's opposite of lenses. You can remember it that way or any other way that you prefer. Now, we've also learned about radius of curvature just now. So radius of curvature is actually the center of the lens. So where the value is actually double the focal length. So your R is double the size or double the distance of the focal length. Or you can also say the focal length is the radius of curvature divided by 2. So this is one way you can identify your focal length value or your radius of curvature value. So again, I'm going to remind you, for sign convention, focal length is negative if it is behind the mirror. It is positive if it is at the front of the mirror. Okay, opposite lenses. Alright, so let's go to image formation of ray diagram. This is also quite similar to lenses, but opposite. Right, so the first step, of course, let's say I'm going to give you concave mirror first. We'll look at concave mirror first. So let's say I have my concave mirror here. Sorry. Let's say I have my concave mirror here. So it hits the surface in a straight line parallel to the axis, remember? And then the focal length it will go through is at the front of the lens, not at the back of the lens, right? And then the second one will hit the focal length again, and then parallel towards the axis, right? So where does it stop? It stops here, somewhere around here. The last one should go through the center of curvature, and then the top of the image, the top of the object. So where the point hits, this will be your image of mirror. And if you still remember, the front of the mirror is the positive value, back of the mirror is the negative value. So meaning positive, the image is real. Okay. Alright, now the mirror also has characteristic of image. The three characteristics, if you still remember, whether it is bigger or smaller, real or virtual, and whether it is inverted or not. So what are the characteristics of this image here? Can you list it down for me? Yes, the first one is the image is bigger and it is inverted as well as real. Okay, very good. So we'll do it one by one. Again, we'll place the object at different position and try to trace the image.